Welcome to the UVSAFE webinar LED 101, Mercury-free UV sources, where we will be covering LED technology, applications, and its relevance to the RoHS directive. Today's session will include two technical presentations, the first by Todd Mikowski of Nichia. Todd has worked in the LED lighting industry for a decade and in his current role at Nichia has backstage access to the development and deployment of UV LED technology. His session will cover the fundamentals of UV LED technology and operation. Our second technical presentation will be given by Babak Adeli, Chief Innovation Officer at Watersprint. Babak has been part of the UVC LED revolution from the early days of low-power devices and niche applications. He has experience in deploying LED solutions across a wide range of applications and scales, and will be talking about the applications in which UV LEDs may be deployed at scale today. First, however, I'd like to introduce UVSAFE. We are a global alliance of UV LED device and system manufacturers with the goal of educating the UV industry stakeholders on the viability and availability of mercury-free UV sources. We believe that the common awareness of mercury-free UV sources lags significantly behind the technological reality. We want to close that gap so that we can transition to a mercury-free UV industry as soon as viable alternatives are available. And as you'll see in a moment, we believe that this is already the case in many applications. The impetus for this webinar series is, of course, the pending expiration of RoHS exemptions 4A1 and 4F4, which cover mercury-based UV lamps. The RoHS directive restricts products containing certain hazardous substances from entering the UV market. Mercury is one of those restricted substances. Fundamentally, mercury-added products are banned within the EU and cannot be placed on the market. However, this is clearly not the whole story. Since certain mercury-added products fulfill critical functions, an exemption system was developed to allow their continued use. Exemptions require that substitution is technologically or scientifically impractical, or where the negative impacts of substitution outweigh its benefits. The critical point here is that the RoHS directive intrinsically tends towards complete removal of mercury-added products from the EU market. Exemptions are temporary measures intended to allow industry to adopt new technologies. What I'm showing here is a brief summary of the timeline for the current process. Exemption extension or amendment requests were submitted last August, and UVSAFE submitted amendment requests for 4F4 and 4A1 at this stage. We're now in the public consultation phase and hope that all attendees will be submitting their evidence and experience to that. ERCO Institute will then aggregate these data, produce a report for the EU Commission, who will then be able to give a decision ahead of the 2027 expiration date. What are we proposing as UVSAFE? The current exemptions are split between smaller low-pressure lamps under 4A1 and a catch-all all other UV lamps under 4F4. Effectively, what this means is that there's no restriction on the use of mercury-containing lamps for UV applications. For 4A1, the lower power low-pressure lamps, we believe that these are entirely replaceable by LED alternatives where only the 254 nanometer emission line is used. We draw a distinction as approximately 240 nanometers, where present-day LEDs emitting longer wavelengths are capable of replacing the functionality of monochromatic low-pressure lamps in all applications. However, we acknowledge that critical functionality is occasionally drawn from so-called ozone-generating lamps, and recognize that shorter wavelength LEDs do not yet provide a viable technological alternative in all cases. Since LEDs cannot yet replicate the function of low-pressure lamps emitting the 185 nanometer line, a carve-out for this functionality is retained in our proposed exemption wording. For 4F4, the catch-all exemption, we believe that this must at least be subcategorized into higher power low pressure lamps and medium pressure lamps so that a meaningful technological assessment can be made. Some lamps and functions for the exemption are easily replaced by alternate technologies, whereas others still justify an exemption. However, the current form of the exemption makes it nearly impossible to make a reasonable assessment, and so we believe that an overhaul in the wording would be required regardless of the availability of alternatives. With that, I'll hand over to Todd, who can talk us through the function and operation of LED devices.
Thank you, Rich, for your introduction. As mentioned, I work for Nichia Corporation. If you're not familiar with Nichia, we're the largest opto semiconductor manufacturer in the world. We invented the blue LED, the white LED, and we've been manufacturing UV LEDs for approximately 20 years. So naturally, my portion of this discussion will be on the LED as a source, doing some comparisons with legacy UVC lamp sources and dispelling some of the misconceptions around UV LEDs. Now, on this slide, we're going to do a quick comparison of lamps versus the LEDs. I'm not going to touch on everything, but I'll hit on a couple of important points. First, UV LEDs are a semiconductor-based technology, which is inherently very robust. Lamps, on the other hand, are a gas arc pressurized tube, which is naturally fragile. From a temperature perspective, LEDs typically operate below 100 C, while lamps can operate in the 100 to 600 C range, which can transfer heat into your application. LEDs are easily dimmed or switched on and off. Lamps, on the other hand, can be dimmed or switched, but it severely diminishes their lifetime. From a cost standpoint, I'll address the elephant in the room. LEDs do have a higher cost per watt than lamps, but they also have a significant roadmap for performance gains and cost reduction as the technology continues to scale. From a lifetime perspective, lamp lifetime is pretty good at around 10,000 to 17,000 hours. LED is similar, with the reported ranges being in the 10,000 to 20,000 range, but that can be further extended by using various control strategies like switching or dimming. Now, what is a UV LED? Well, it's a small semiconductor device that when current is applied across it, it emits UV light. Now, at an electronics standpoint, it's incredibly flexible. These can be built into small arrays that are low voltage all the way up to really high voltage systems. And then from a control strategy standpoint, anything that can be done in a general lighting like a white light or display application can be applied to a UV LED because the technologies are very similar. LEDs are tunable. Now, when I say tunable, I don't mean that you can vary the current, it changes the wavelengths, but at a production level, you can vary the wavelength by varying the chemistry inside of the semiconductor material. If you look at that graph there, you'll see indium gallium nitride in that blue range, and then right above it, you'll see aluminum gallium nitride in the top range. Aluminum gallium nitride is the chemical makeup of a UV LED. Indium gallium nitride is the makeup of a blue LED. So just by making that change from indium to aluminum, we can go from producing a blue LED to a UV LED. And then by varying the amount of aluminum inside the semiconductor, we can change the wavelength of the UV light. LEDs are very small, so typically around 3.5 millimeters on their own. This allows them to be used individually for space-constrained applications or low irradiance applications, but more importantly, they can be built into large multi-kilowatt arrays. And this is really important because when we hear people talk about lamps, they say, how are you going to replace a 1,000 kilowatt lamp? Well, you don't replace it with a single LED. You replace it with an array. And the theoretical maximum of the array is limited by the power source, not the number of LEDs. So you can build, an absolutely massive UVC LED system if you want to. It just comes down to the application and not the individual source power. LEDs have directional emission, which means the light comes out of the front, typically in around the 120 degree range. This is really important because it means you're projecting the light forward just towards your target surface or fluid. So from a system perspective, this is a massive advantage when you compare that to an omnidirectional light source like a lamp, where you're going to have to redirect that light back towards your target in a lot of applications. And anytime you have to redirect that light, you're introducing losses at a system level. Just like they have directional light emission, LEDs also project heat out of the back. So you have UV light coming out of the front and the heat comes out of the back of the package. This is beneficial from a system perspective because it reduces the process heat impact. So because the heat's going out the back, it's not going into the water or projecting down onto the surface, the chemicals that you're working on. And finally, talking about their lifetime, LED's lifetime is very stable and predictable. That's something that we've seen for 30 years in the white LED space, but even in the UV LED space, what we typically see is a slow, steady degradation of the light output. But even if failures do occur, there are plenty of electrical and optical strategies for monitoring those outputs and ensuring that the system's operating safely. Really what I want to point out on this slide when we talk about what wavelengths can be covered, anything from about 230 nanometers to 405 nanometers is being produced, or if it's not being produced, it's really a question of commercial demand versus technical feasibility. And when we compare that to the lamps, here we're showing a medium pressure lamp, which is the green polychromatic line, or a low pressure lamp, which is the black, almost monochromatic line at 254 nanometers. Those wavelengths that are produced by the Mercury technology are not unique. There's nothing special about them. They're just a result of their chemistry. And anything that can be produced by the lamp from about 230 nanometers and longer is already in production or can be produced. So there's no secret sauce to the lamps at all. Now diving deeper into the wavelength, on this slide I want to split this into a comparison between two technologies. Medium pressure lamps, that was the polychromatic spectrum we saw on the previous slide, versus the LED. This will be the graph in the upper left, and then I will also compare low pressure lamps, the black nearly monochromatic spectrum from the previous slide. This is primarily used in disinfection, so we'll compare disinfection efficiency of the available wavelengths. Now first, diving into the medium pressure, we'll be looking at the graph at the upper left-hand side. The main argument for the continued use of medium pressure lamps, which make up about 30% of the UV lamps sold today, is that these lamps are highly radiant dense and they produce a lot of peak wavelengths, allowing the end users to select what they want and filter out the rest. And while this is true, these lamps are quite radiant dense. When we compare them with commercially available LEDs today, we can see that in the range from 270 nanometers to 405 nanometers, the LEDs are already a more radiant dense source. In addition to being more dense at the source level, the LEDs are also more efficient at converting that energy into UV light, especially within that 270 to 405 nanometer range. Now, another point to clarify on this is reactions have an absorption curve, not a point, right? So even if the peak absorption of your reaction is, let's say, 255 nanometers, it's likely that a 270 nanometer LED could provide enough energy to still complete that reaction, or the chemistry of the reaction could be tuned to work with slightly longer wavelengths. So for any application where the primary benefit is from energy within that wavelength range of 270 to 270 to 405 nanometers, I think this graph should greatly diminish the argument for the continued use of medium pressure lamps, because within that wavelength range, the LEDs really are the more efficient and dense source. Now moving to the table on the lower right, here we're going to be comparing the germicidal efficiency of a 254 nanometer lamp to a 265 or 270 nanometer LED. What this table shows is that because the LED's wavelength is closer to the germicidal peak, which tends to be in that 265 nanometer to 272 nanometer range, the LEDs have a higher germicidal efficiency than the 254 nanometer lamp. And what that really means is that for the same energy applied, the LEDs are providing a higher level of disinfection. Another benefit of an LED is that it can be designed towards specific pathogens, meaning if you were targeting, let's say, rotavirus, and that pathogen has a peak of 268 nanometers, don't quote me on that, I don't know exactly what the peak is, but you could use a 265 to 270 nanometer LED, which is very close to that peak, and align with that peak absorption range, where with legacy lamps, you're just stuck with what that chemistry produces, which is 254 nanometers. So that would mean you would actually have to apply a higher dose, which could potentially mean a higher input energy. That really comes down to the system wall plug efficiency and the different technologies, but ultimately what it means is that in that specific pathogen application, the LED would be more efficient. On this slide, we're going to be talking about the UV LED's improvements over time, but before I get into that, I really want to touch on and explain that even based on today's wall plug efficiency, today's cost, today's everything, UV LEDs are already being commercially adopted in everything from municipal water, commercial air, to medical applications, the technology really is being adopted today and is very viable at current performance, cost levels, everything. So while I am talking about improvements, I don't want to frame this as LEDs are a future technology. They are getting better in the future, but they're great today. Now, looking at these two graphs, we're going to start on the graph on the left. This shows 20 years worth of data provided by AquiSense, outlining how LEDs are continuing to follow Haight's law, which essentially means that for every 10 years, the output of the technology doubles. And you can see from that graph, LEDs have continued to follow that trend. Additionally, looking at the graph on the right, this is showing external quantum efficiency levels. This is showing that all throughout the wavelength ranges that we've talked about today, LEDs are already putting up very respectable levels, and this graph was produced in 2005. I believe if you check that today, you'd find that these numbers have even improved despite this only being a year old. So it just goes to the rapid advancement of the technology. Now, why this matters is because the lamp is saturated from an efficiency standpoint, and the LEDs are rapidly catching up. This means that we'll see a convergence of wall plug efficiency between the lamps and the LED fairly soon. My estimate is that we'll probably see a convergence with medium pressure lamp efficiency within the next 3 to 4 years, and a convergence with low pressure lamps within approximately 10 years. While I don't see the convergence of wall plug efficiency as necessary for the technology to be viable, especially considering that from a system level and a wavelength perspective, there's a lot of benefits to the LEDs, I do see this as that this is important from a regulation standpoint. And with that, I'll give my point. Given the aggressive evolution of LED and the necessary time to design, test, and certify UV systems, paired with the relatively slow process of environmental regulation, it seems critical to me that we strongly review whether there's a true technological demand for these exemptions or a reliance on legacy technology for enhanced profitability. Frankly, it's my belief that considering the rapid technological growth from UV LEDs, the majority of the support for exemptions come from the latter and not the former. So I hope that if there's anyone attending today's webinar that is in the review process, you strongly consider that, because really this technology is viable and I don't believe it's being applied as broadly as it could be. Finally, we want to talk about the scalability and supply chain of UV LEDs. In those images, you can see Nichia Corporation's headquarters on the left and Osram on the right. We are founding members of UVSAFE, and we're also two of the largest opto semiconductor manufacturers in the world. So we can speak with some authority to the supply chain and scalability of LEDs, because we saw it happen with general lighting and we're seeing it happen in real time with UV LEDs right now. A couple of key points here. When we talk about the global production of LEDs, and I mean all LEDs, white LEDs, UV LEDs, color LEDs, globally that production is approximately 1 trillion LEDs per year. Now, the important point that I want to make with this is that the fundamental production of a white or traditional LED, visible LED, is not a dissimilar process to producing a UV LED. As I showed in that second slide or third slide, it's really just about varying the chemistry. The rest of the production process is about the same. So because the production process is the same, there's not a major barrier for a manufacturer like Nichia or Osram to move production to UV LEDs. Additionally, based on the estimated total number of UV lamp optical watts in the market today, if we needed to replace every single Mercury lamp today, we would expect that to be about 350 to 700 million LEDs annually that would need to be produced, UVC LEDs that would need to be produced. When you think about the global production scale being 1 trillion LEDs annually, 350 to 700 million LEDs is really nothing. And I think from both Nichia and Osram's perspective, we believe that we could absorb that kind of demand increase on a really aggressive timeline, probably in approximately 2 years. So the point of this whole slide, manufacturing capacity is not an issue. Now, I appreciate you all listening to me, and I am going to turn it back over to Babak to talk about UV applications that are being implemented today. Thank you.
Thank you, Todd, for a great overview on the state of UV LED technology. As Rich introduced me earlier, my name is Babak and I'm from Watersprint. For those of you who may not familiar with Watersprint, we are designer and manufacturer of UV LED water treatment systems with operations in Sweden and Canada. Well, so far we have focused on the technology itself, as Todd presented, how UV LED works, how they have evolved over time, and how they compare with the traditional mercury-based UV sources. And we saw at the light source level that LED can either be equivalent or superior source for various applications. Now, the important question is, where are these technologies being used today? Which I will try to present very briefly some of the examples at the application level. To begin, let's look at the overall technology readiness landscape. You probably have seen a chart like this before. This chart provides a high-level view of major UV applications mapped against their operating wavelength ranges and the current readiness of UV LED technology, which is added to the best of our knowledge and state of the technology. One of the most common misconception is that LED is still emerging technology. That may have been true likely more than 20 years ago, for example, for UVA and UVB applications, and perhaps 10 to 15 years ago for UVC, but it is no longer an accurate description of the industry today. As also Todd explained in part of his presentation. In UVA, basically between 315 to 400 nanometer applications such as curing and industrial processing, LEDs are already highly mature, broadly commercialized, and in many cases are the option of the choice. LED devices also right now available in the UVB applications, basically between 280 to 350 nanometer emission band, like sensing, agriculture application, and phototherapy. In UVC range, mostly around 255 to 280, the wavelength definition of the UVC is a wider spectrum, but for disinfection, specifically for LED, between 255 to 285 nanometer, the dominant application is disinfection for water treatment, air disinfection, surface disinfection. The technology has progressed well beyond the research and development. Today, we see commercial certified products, large-scale manufacturing, and extensive deployment across multiple sectors. In fact, UV LEDs have enabled entirely new product categories. For example, in appliance integration, point-of-use treatment system, and compact disinfection, where conventional mercury lamps were often not practical. At the same time, there are remains applications requiring wavelength below approximately 240 nanometer. The area on the chart that shaded as red with the tag under development, where commercial LEDs remain limited and the development continues. So the key takeaway from this chart is that UV LED should not be viewed as a single technology at single readiness level. There are different application regions based on the wavelength and readiness of the technology that we can point out, and we try to focus on these regions more. But before moving to the examples of application, it is important to discuss how UV technology should be viewed. Historically, there was comparisons between the mercury lamps and LEDs focus on a component level metrics like optical power output, wall plug efficiency, how to operate the device. These are a good metrics at the component level, but they do not tell the full story to us. ultimately, consumer do not buy LEDs. Consumer do not buy mercury lamps. They buy systems, and systems performance depends on much more than efficiency of a single light source. It depends basically on many other factors. For example, optical design, thermal management, reactor geometry, the use of reflective material or not, the control system that operate that system, the switching behavior, the on-demand behavior that LEDs offer, the required maintenance and lifetime performance of a device. You may hear that LEDs typically operate at efficiency below 10%, while the low pressure mercury lamps offer exceeding 30%. This is what Todd also mentioned in his presentation. That statement is generally true at the source level, but it does not necessarily translate into the superior system performance. The directional emission of the LED, the compact size, the flexible layout and high energy density of the LED chips, and the ability to integrate advanced optics and reflective material in an LED system. As you can see in the image up there, that one single LED can be modified to emit in a wide range of radiation pattern, and that enables advanced reactor design for LEDs, allow UV LED system to achieve significantly higher system level efficiency than would be expected, for example, for an equivalent mercury lamp. The example of the table basically point out to this, where one LED device, Watersprint Aqua Aromax home device, using two different LEDs compared with two commercial low pressure mercury lamp devices. The lifetime of LED device is more than 10 years based on the data in the field. For 10,000 hours of LED, because of the intermittent use in a residential market, the equivalent lifetime for the UV lamp devices are roughly around 1 year. Even though the Watersprint device uses two different type of LED, one with 2% wall plug efficiency and one with the 6% wall plug efficiency, you would expect that based on this power consumption, the performance should be significantly lower than equivalent power consumption for the mercury lamp. But we in fact see with the lower wall plug efficiency, the Watersprint Aqua Aromax home device delivers a higher performance equivalent NSF55 class B flow rate compared to two other conventional mercury lamp. The reason is simple, because the system efficiency is not determined solely by the source efficiency, rather by the design flexibilities that LED offer at the system level. This system level perspective is essential to look at when we are reviewing LED devices. Now, let's return to the application landscape and look at it through the lens of the wavelength. This slide basically provide an overview of major UV application categories and wavelengths. Ranges typically used to achieve the desired process outcomes. Disinfection is concentrated primarily on a UVC range, typically for LEDs between 250 to 285 nanometer, although some application goes beyond this wavelength. Phototherapy is generally centered around narrowband UVB wavelength, most commonly around 311 nanometer. Today, we see LED devices that, with some deviation from 311 at 308 and 315 nanometer, demonstrated excellent clinical effectiveness. Curing application spans a broad range of wavelength typically because of the chemistry involved in the process, but predominantly UVA is the wavelength in use. This is the area where LED technology is already highly mature, widely commercialized, and is a light source of choice in a majority of applications. We also have photocatalytic application where ultraviolet radiation activates semiconductor material. The most commonly known is titanium dioxide. These applications basically use for contaminant degradation, advanced oxidation, even some emerging technologies related to carbon capture and solar fuel generation. Most of these processes are driven primarily by UVA wavelength, where LEDs are widely commercialized and available. And finally, there are applications involved direct photolysis and ozone generation and advanced oxidation through photolysis, which typically require wavelength below 240 nanometer. With the exception of this last category of photolysis and ozone generation, the wavelength range required for all the other applications are well commercialized by LED. Todd shows this. We try to go to each of them and show that actually at the system level, the product exists for this category. Let's start with the water disinfection overview. The water disinfection represents the largest UV application and one of the most important markets in the context of this discussion. Water treatment can broadly divided into three segments. The first is point of entry, point of use, and point of entry systems. These are typically residential, condos, offices, commercial space, and decentralized treatment system, and historically have relied on a smaller low pressure mercury lamp, typically exemption under 4A1. The second section is for commercial industrial devices. These range from food and beverage system, transportation, marine application, public dispenser equipment, industrial processing, and eventually a third segment, which is the largest in the capacity, historically relied on the high power, low pressure mercury lamp and medium pressure mercury lamp, which are municipal system, wastewater treatment system, and those are under exception of 404. The distribution between these three classes are deployment today, more than 70% are for point of use and point of entry systems, 25% for commercial and industrial systems, and less than 5% for municipal systems today. Now let's see some of the example of deployments. We have household and commercial appliances with the flow rate less than typically 15 liters per minute. We do have analytical and commercial devices as well as public water stations up to 20 liters per minute, and the devices over 20 liters per minute up to 60 liters per minute for residential, commercial, and industrial application for this category. And I think looking at this installation, this is where the discussion shifts from technology readiness to market reality. Please note that just the appliance integration alone, which was mainly enabled by LED, has enabled deployment of hundreds of thousands of UV LED devices across only UVSAFE members company. The examples shown here are not, any of them are not laboratory demonstration or pilot projects. These are commercial systems operating today in homes, commercial facilities, transportation system, industrial environment, and public infrastructure around the world. In many cases, particularly in residential point of entry and industrial applications, these systems are direct replacement of traditional mercury UV systems, mostly in a 4A1 category. What are the main market drivers? First, the on-demand operation of LED. Basically, this is multiplies the lifetime. There is no warm-up period. There is no delay in the treatment. This is specifically good for intermittent application, which dramatically reduce the power consumption, reduce the fouling because of the heat accumulation and maintenance requirement. And as I mentioned, it extends the lifetime significantly. LEDs are inherently compatible with low voltage DC operations, so this making them attractive for solar power, battery powered operations, and also transportation, outdoor installation, and developing regions. And finally, their compact size enable direct integration to the appliances, which I mentioned that is one of the largest volume of deployment to date. Combined with the elimination of mercury itself, and the increasing regulatory pressure, including RoHS, these factors have accelerated basically the adoption of UV LED devices in many application sectors. We have seen that in the smaller point of use devices, and we see it today on the point of entry commercial and industrial systems. Of course, technology adoption is ultimately driven by regulation and economy. The good news is that the characteristic that makes UV LED attractive do not create barriers from regulatory or standard perspective. Today, UV LED systems are compatible with all major performance and safety standards across the water industry globally. For example, from just members of UVSAFE, there are numbers of NSF 55 certified product. There are ongoing development under DIN 19294 and DVGW framework, and emerging European standard specifically addressing UV LED performance and monitoring under EN framework that is expected by 2027. These are regulations related to the performance of product. There are other compliance under device material safety or structure integrity, which are ultimately engineering requirements, and UV LED system have exhibited compliance to these standards. From economic perspective, there is no barrier either. The table on the top right basically shows the acquisition cost, maintenance, and energy consumption cost for conventional low pressure mercury lamps and UV LED system for three categories of point of use, point of entry, and commercial, light commercial industrial applications. And while there can still be acquisition cost difference between LED systems and mercury-based systems, operation and maintenance costs are often significantly lower. So this is particularly true for intermittent use applications, which represent a large portion of the system historically served under 4A1 exemption. As you can see in the field data at the bottom left of this slide, these are actual residential installation data of Watersprint Aeromax home system operating on an average duty cycle of 6% compared to the conventional mercury lamp, which are typically operate continuously 24 hours a day, 7 days a week. The combination of reduced energy consumption, lower maintenance requirement, and longer service life often result in a payback period between 1 to 3 years from point of use category all the way down to light industrial, while system lifetime expected to be more than 10 years. So given the advantage of LEDs and the compelling return of investment discussion here, we do see more and more distributor, dealers, partners, integrator who decide to basically switch completely from conventional mercury systems to LED system, because this eventually benefit the user and they see a better future with the LED devices. Now that we reviewed the point of use, point of entry, and commercial and industrial system, the question is, can UV LED address large-scale application historically served by large low pressure and medium pressure mercury lamp systems under 4F4 exemption. What are the main applications in this category? Basically, they are drinking water, food and beverage, advanced oxidation processes, industrial process, wastewater reuse, and discharge. The answer is yes, they're getting there. This slide provides some examples of large-scale UV LED deployment from installation completed by AquiSense. These projects demonstrate that UV LED technology is already being applied in applications that historically relied almost exclusively on conventional mercury UV systems. In some cases, these are entirely new installations. In others, they represent direct replacement of mercury-based system because of some of the operational maintenance advantage offered by LED. The significance, to my opinion, of these projects goes beyond just an individual installation. They demonstrate the direction of the market. And basically, that is the basis for the distinction we have proposed between low pressure and medium pressure mercury lamp within the current 4F4 exemption framework, with the possibility of a future review in 5 years that allow UV LED technology progress, commercial deployment, and operating experience to be evaluated against those larger scale applications. Moving beyond water treatment, UVC LEDs are also seeing broad adoption in air and surface disinfection applications. Same as water treatment, the science of disinfection is fundamentally driven by wavelength and dose delivery. There are some examples of LED products shown here. Basically, the upper room UV. These are the fixture mounted above the occupied space, and the directionality and modification of LED radiation is a specific advantage for this application. We do have induct HVAC that basically do air disinfection, protect of the cooling coil, and also sometimes protecting the air handling unit. And these could be very energy efficient because of the instant on-off characteristic of LEDs. And eventually the enclosed surface chamber, that these could be for various application, wide range of application these days. We see from cell phone to VR headset, tablet, medical devices. You've seen many examples of these, and there are design flexibility because of the LED size and also radiation pattern. We do also know that today wide range of UV LED product available in similar application. Those are including the transportation system because of the solid state and robustness of LEDs. We see LEDs more and more in the healthcare environment for surface and air disinfection, and portable disinfection units that become more broadly adopted these days. Many of these applications benefit directly from the unique characteristic of LED technologies. The drivers are very similar to water treatment. The compact size of LEDs allows them to integrate into locations where it wasn't practical for a conventional mercury lamp. The instant on-off operation of LED basically give a dynamic operation of the devices to occupancy, to airflow, usage patterns, and the absence of mercury simplifies integration of these devices to the consumer product or to the healthcare facilities and sometimes the food processing facilities. Moving to the curing is a different category than disinfection. UV curing is actually one of the strongest example of LED broad adoption, and one of the clearest demonstration of how quickly a UV market can transit once LED technology reaches a certain point. Curing applications are predominantly UVA based and operate across a range of wavelength depending on the chemistry of the being used in the process. Today, UV LED curing is widely deployed across printing, coating, adhesive, electronics, manufacturing, automotive applications, packaging, maybe industrial product processing. So very broadly is being used in many of these sectors. LEDs have already become the preferred technology, mainly because they offer lower energy consumption, reduce heat generation compared to conventional mercury lamp, longer operation lifetime today for the UVA LEDs, and improve process control and significantly lower maintenance requirement. One another I would add is also that the wavelength of LEDs could match and optimize a process in the curing, where again the wavelength coming from the science of mercury was necessarily available, but not the optimized one. LEDs giving us an avenue to optimize these processes. And in many cases, manufacturers have redesigned the production lines around LEDs because they see benefits beyond simply replacing a lamp, rather to optimizing the process. The final application category that I have here includes phototherapy, scientific instruments, basically analytical devices for calibration and specialized uses. As we discussed earlier, many of these applications already operate successfully with UV LEDs today. In phototherapy, LEDs are being used at UVB wavelength band and have demonstrated very strong performance in modern treatment devices. Also, the scientific instrument increasingly benefit from the wavelength specific emission of LEDs, stability, their compactness, their controllability. At the same time, this category also maybe highlights an important point, which may be different from other applications. Some medical and scientific applications have highly unique regulatory paths, or sometimes the science behind these applications are highly unique, for example. And that is precisely why the RoHS framework already contains a dedicated mechanism through Annex 4 to address these specialized cases. That means where a legitimate technical or medical needs continue to exist, there are a regulatory pathway available to accommodate them. These specialized applications should be considered on their own technical merits rather than being used to justify broad exemption for all other applications. So for this class of product, if there is still medical or scientific use exists, Annex 4 of RoHS exemption exists to grant them exception for a certain period of time. That was the last slide. We thank for the opportunity to present some of the features of UV LED technology and readiness at the application level. And we look forward to hear your questions. Thank you.